Okay, the second of 4 figures, and then as well for the first figure, and it's almost so Jiang can um, Hi, Jiang, can you hear me? Yeah. So this is our first session, and let's welcome Jiang for his presentation. So now it is yours time. Thank you. Maybe what you say that way? Yes. Okay. My name is Zhang. I come from Baixin University. This work is done together with Yang Zhao, Ying and Jiang. I will talk about what people Sinkhorn-CPD. It's a robust method for point cloud migration. Okay, let's start. This is Gaussian. Mine all have 4 parts. The one is a background to the restriction, but 2 we have some fashion. One has a transform method city field. We use the theorem to constitute. Part 3 is our method. Part 4 is the experiments. Let me explain this first. This is a common task in CAD and manufacturing. We have real parts, we have a 3D scanner to scan it. Then we get a point cloud. Next, we want to put this point cloud onto the CAD model. In industry, people use this task to check the quantity of the parts and also review this model. In math, the flow is this. We want to plan the rotation R and our translation T. After this transform, the 2 point clouds match where. If the date is clean, the problem is easy. But the red scan date is not clean. It has recurrence. Problem 1 is weight. Every point move a little bit from the original surface. Problem 2 is diffusion. The scanner cannot see the full surface, so some parts are missing, and the overlay is no special. Problem 3 is analyzed. There are wrong points. They come from the background reflections. These are and overlap. They can make the whole result wrong. Now, I will introduce one important key in regression. Regression is one of correspondence. That means which place matches which place. Why? Because if we know the matrix, then R and T are easy. They will have a solution by SVD. So some methods differ in following boxes how to set the weight W. The system is SAP. Each point X is a nearest number, but this hard trace as follows. When the date has noise, the matrix often jumps. When the sign force is bad and the initialize is bad, SP will on the wrong matrix and it cannot go back. Now CP gives a better answer. It does not make a harder choice. It makes a softer choice with probability. The model is a conceptual model. It uses a softer correspondence is a posterior probability. In this formula, when 2 points are close, the weight is large. When they are not, the weight is small. Please remember the 2 things. First, each data point gives 1 unit of mass. It spreads the mass over the source points. Second, where sigma squared controls the sharpness. The sharpness is large, the weights are soft. Sigma is small, the weights are sharper. And sigma updates itself with this formula. CPD goes from to sheet, step by step. We call this unarranged. The second goal is smart transport or OT. OT is about the moving mass. So first is mass. The flashpoints also have mass. The transport and gamma tell us how much mass moves from the point M to point N. Please notice such a correspondence matrix is exactly a transport plane. They are easy with Entropic. This problem is easy to solve. We can use simple operations that are simple and fast. Here, the epsilon works like temperature. It controls the sharpness of the pen. Even already have used OT for registration. For example, RPOT or ROPOT. They also share this form, but the two choices have no expectation. Question one is the cost. Why not the squared distance? There is no theory for it. Question two is the temperature. We must turn epsilon by hand for every distance. If it drops slowly, this method is slow. If it drops fast, the method gets fast. Furthermore, we answer the question. The balance theorem, let me show the figure. This is a 2D example. The gray curves are outlined. Here, more than half of the points are outlined. Look at this result. CPD fails company. The error is 2000 even grades. Look at the bottom group. It shows the power of each point. We call it volts. Red means strong volts. In the city picture, outline their rate. It means they vote their votes, put their roles to optimize. So they could results away. So here is question: why does this happen? Here is our main results. Summary one says the E step of the CBD exactly empirical automata transport problem. In this problem, the close is square distance. The temperature is 2 sigma squared. The cloud measures are fixed. The row measures is weight. The other one, CBD, is doing optimal transport all the time. This must teach us two things. Thing one, it explains the value. The plan constraint says every touch point must receive 1 unit per mass. It includes every outlet. So we never turn off optimize. This is the true rule of this problem. Thing two, it gave us the right design. The code should be the Gaussian root of height. No likely. The temperature should be 2 sigma squared. They are exactly answer to the question before. Now let me show this with numbers. The root of the point is shared in the total mass. It won't means far from the results. On the plan country, every optimized must be of 1 unit in weight. The soft assignment is very this way. But I cannot make this way smaller. The total is always 1. In this example, optimized was 47.5% of almost more than half. The result is wrong. Now the fix is clear. We show that the mass of the 5 points go to 0. This is our method. We need two things. This change comes from the silver. Tenglong. We remove the hard constraint. We use scale penalties instead on the side. What does scale penalty do? It allows the mass to change, but with a cost. For an outline, there's no good match anywhere, so it's cheap to pay the cost. Then its mass goes zero. Outline is cut off. Change two. We use a Gaussian black hole as a host. So, the automatic underlying of CPD is key. Look at the bar on the right. Outline will drops from into zero or one thing. The diplomas experiment tau equals 1 volt for all experiments. We do not need turning the experiments. Here is the Opaque one. It's EM, the same CPD. In the E step, we build the code matrix and we run general Sinkhorn declaration. This gives us the transport M step. We solve a problem with SVD. It will give us the R and T. Then we update sigma. Look at the bottom three. The start, the pen is solved. Then the sigma harmonized and the pen becomes a clear diagonal line. This line is a great matrix. Every step has a closed form solution, so it's fast. A few talks in the algorithm. The flow is a diagram push and pull. Various updates. Then loop. Each step is falling to scaling steps. We can repeat them in a few times, and it's easy to implement, and it can run fast on the GPU. And again, we do not need turning the elements. We can just say the tau x equal tau y equal 1 for all experiments. Here we show the temperature and the ceiling of objects. The three lines are the temperature of each method. The dashed line are the true result. This means the real distance between the match and the match points. Good temperature should follow the result. If the reason is large, it stays short. When the reason is small, it becomes sharp. We can see the CPD is a blue line. It drops too fast and it becomes sharp too early. So it blocks in the raw matches. Our BUT and RPOT do not look like the data one. The government original follows the rest of. So we can say that the date for method are date drivers analyzed. Now here is transport and evolution. There is same story from the other view. There are transport metrics during the iteration. On the right side is the dashed line in the online lines. This is one top line, and the left is the true the inlines. The top line is CPD. We can see that the top line lines they are dark white, and the constraint keep mass in the because they must have set the all plan units mass for all the clan. Now the middle is RPT, RPT. It has a better result, but still weakly. The bottom is one method. After 25 iteration, our pen is totally clear. It shows that our method can remove the outlines clearly. Here we compare our method with three papers, and our beauty is needs 21. It fixes the XML and fixes the row. Their terms are fixed, and in CGF 22, their XML are designed by marking one 0 to 9. And all methods are for three like things. Here is four experiments. The first one is the test in the sample body. In the latter slot, we increase the interval. The is CPD. And it fails after 20%. And the original experiment method always stay in the bottom. Means it's not good results. This we can see in the overlap rates, when even with 70% compromise, oil method still give good results. There is our experiments in the model line 40. The second, we can say that this dataset has 40 categories. We add noise and plugin to the original data. And in this experiment, our method reaches the best results. And even better than the GeoTransformer and RPMNet. There are many methods, and they are trained in the data. Our methods are not need to train. Now here is we test it in our real application. So we cluster 40 industry parts and we get the income, and then we to reject it, use our method and test for the method use the Baixin method. And we can see our method still is the best, and due to the futures the Congyi and Jiang get many errors. And we go to the population. The 10D, we get the intensity to tau x and tau y. We can see that in this picture, our results are not changed very big. So it means we use x equal tau y is 1 everywhere, and that is okay. And in the B, we test the downside here. It means that our downside here is the best. And in the picture C, we test our sigma form is really useful, and the result shows that our design is the best. And in the part B, we show that if which tau y equal 1 or other thing will be different. The result shows that when the overlap is more than 60% it's true and no difference. And when the overlap is low, we can choose y equal 0.1 will be better. And then when we will conclusion, and Inversion. This will build a bridge between CBD and automatic transport. Plus, the third one expand YCP bills, and one set constraint both outlines to keep the mass. Second, the base is simple. We use scale energies on both sides. Then the optimized mass goes to zero, and variance step still close for. Three, the variance is the temperature, so the analyzing is automatic and there is no time. In the future, we are planning to extend this method to non-rigid restriction and to large point clouds. Now here is the main reference. That's all. Thank you very much. This paper, this is the paper link and our code and our benchmark code are open in GitHub. You can see the QR code here. That's all. I have to hear your questions.
Thank you for Ying's presentation. Any questions? So I have a question. So sometimes in practical, we may have multiple point clouds, not just the two pair. So how can you deal with multiple point cloud registration? Just you need can you do some joint optimization for a multiple point cloud, like more than two?
There was restriction that only allow one point to another point. And the only want to use it in multiple restriction, we always use the um, fields to restore align, and then align the two icons, and then align two icons. And finally, we got the multiple registration, but it's a simple idea. There are more ideas such as when we design together, we will use other methods such as list square to minimize um, all to get results, better results.
Okay. So thank you for the explanation. And any other questions? Okay, thank you, Jing, for your presentation. And yeah. So let's welcome next presentation.
Wait. ，Good morning, everyone. Today I will present our work, PointInDI, Inversion by direct iteration for high-fidelity point cloud denoising. The main goal of this paper is to recover clean and detailed point clouds from lost 3D scans. In this talk, I will first introduce the denoising problem and the limitation of existing methods. Then, I will explain our PointInDI framework, followed by experimental results on both synthetic and real-world datasets. Let us begin with the introduction. Point clouds are widely used in 3D vision and graphics. As shown on this slide, They support applications such as autonomous driving, digital cities, virtual reality, industrial design, 3D printing, and game development. Point cloud data is mainly acquired from scanning devices such as laser scanners, lidar sensors, and connected depth cameras. Although these devices have improved repeatedly, loss is still unavoidable because of sensor limitation, object materials, lighting conditions, and environmental influence. Its loss not only reduces visual quality, but can also introduce errors into little geometry processing steps. This is why denoising remains a long-standing and fundamental problem. The key challenge is that point cloud denoising is an error-poster problem. A single noise input more corresponds to multiple plausible clean surfaces. Therefore, a good denoising master must do more than simply move points to nearby positions. It should suppress loss, avoid regression to the mean, and over-smoothing, and at the same time, process sharp edges and fine geometric details in unordered point clouds. Balancing its objectives is difficult. Next, I will briefly review the most related methods. Single-step deep learning methods directly map a loss point cloud to a clean one through a single forward path. For example, point filter incorporates geometric information to better preserve shape features, where SDN treats denoising as entropy recovery and use an adaptive stopping stretch to reduce over-smoothing under high loss. These methods are usually efficient and simple. However, when trained with distance-based losses, they tend to predict an overshot solution, which kills regression to the mean artifacts and may blow sharp details. Multi-step methods try to alleviate the regression to the mean problem by refining loss point cloud. So multiple stages. For instance, iterative PFN use a multi-stage architecture with intermediate separation and straight PCF, most denoising with straight pace flows. These methods can improve detail recovery because they decompose a harder inverse problem into several easier sub-problems. However, they often introduce higher computational cost and more complex architectures. This slide is our motivation. In multi-solution regions, a single-step regression tends to converge to the conditional mean of all possible clean shapes. As a result, high-frequency geometry is sensible. One shot regression to a multi-step feedback process. We construct a degradation path from clean to loss point cloud, and down in inference, we reverse its path step by step. In this way, complex denoising is decomposed into either local restoration problems. Our contributions are threefold. First, we propose PointInDI, a new iterative point cloud denoising framework based on the inversion by direct iteration paradigm. Second, we introduce a continuous degradation path in point cloud space, together with a time-conditioned network for progressive refinement. Third, so extensive experiments on statistic and real-world datasets, we saw that PointInDI achieves state of the art of highly competitive denoising performance while preserving geometric details. Now, let us move to the method. We first analyze why single-step regression may fail. Under distance-based losses, such as squared error or chamfer-like losses, the risk minimizer is the posterior conditional mean. This is optimal when the posterior has a single dominant solution, but in point cloud denoising, the posterior can be multimodal, especially narrow edges, thin structures, and ambiguous regions. In that case, the conditional mean reaches different closable surface, producing broader geometry and loss of details. This is the regression to the mean effect. Here is the overview of PointInDI. During training, we randomly sample a degradation level T, constrict an intermediate state between the clean point cloud and the lost point cloud, and train a time conditioned unit to predict the clean state. During inference, we start from the loss input at T equals 1 and perform estimatic update steps. At each step, the network predicts a clean estimate, and a closed form update moves the current state towards that estimate. This gradually reduces loss and mitigates regression to the mean. The first component is the continuous linear degradation path. We define T as the degradation level. When T is 0, the state is the clean point cloud. When T is 1, the state is the fully lost point cloud. For any intermediate T, we linearly interpolate between the clean and lost states. This gives the model especially guidance about how geometry degrades from clean to loss. More importantly, it provides a simple path that can be reversed during inference. The denoising network is conditioned on both the intermediate point cloud patch and the scalar degradation level T. Its backbone follows a unit-style encoder-decoder design, which is effective for multi-scale feature interaction. The time value T is encoded and injected into point features, allowing the network to adapt its prediction to different loss levels. Therefore, the same network can handle states near the loss end, intermediate states, and states close to the clean surface. The restoration process is divided into as discrete steps, and the step size is delta equals 1 over s. At iteration I, the degradation level is T equals 1 minus I times delta. So T gradually degrades from 1 to delta. At each step, the network predicts the clean point cloud from the current estimate. Then the closed form update combines the current estimate and the predicted clean state. As T becomes smaller, the update relies more strongly on the clean prediction, and at the final step, the current state is directly replaced by the predicted clean point cloud. The inference algorithm is simple. First, we interlace the current point cloud with the loss input and set the number of refinement steps. Second, at each step, we feed the current point cloud and the current T into the time conditioned network. Third, the network predicts a clean estimate. Fourth, we apply the closed form state transition to update the current point cloud. After all steps are completed, the final refined point cloud is written as the denoised result. During training, the network is supervised to recover the clean point cloud from an interpolated degraded state. For each closed knot pair, we randomly sample T from a uniform distribution between 0 and 1, constrict the intermediate state, and ask the network to predict the ground truth clean patch. The loss is an L1 loss between the prediction and the clean point cloud. This objective encourages the network to learn restoration at every degradation level, which is essential for stable iterative inference. Our method is guided by a clean degradation process and has a simple, more efficient network. Next, we evaluate PointInDI experimentally. This slide shows visual conversions on the PureNet dataset. The color map indicates the point-to-mesh distance, where blue means closer to the ground truth, and orange means more north. Compared with the baselines, our result contains fewer orange arrow regions, and better preserves the overall shape, sharp boundaries, and thin structures. It demonstrates that PointInDI can remove noise while maintaining high-fidelity geometry. Here, we saw results on the real-scanned connected dataset. Real sensor noise is more complicated than synthetic Gaussian noise. In contrast, our method generates cleaner and more uniform point clouds. We also test on indulgence. PointInDI generally well to answer real-world indoor data, not only to object-level statistic benchmarks. This slide presents outdoor results on a street dataset, as shown in the highlighted regions. Our method removes heavy loss while preserving the structural shape of objects. After the visual conference, we further report the quantitative matrix. We use chamfer distance (CD) to measure the bidirectional distance between the denoised point cloud and the ground truth point cloud. We also use point-to-mesh distance or P2M to measure how far the denoised points are from the ground truth mesh surface. This slide shows the results. So the quantitative results on the PureNet benchmark on the different resolutions and noise levels. Overall, PointInDI achieves best or highly competitive performance across more settings. This slide shows the quantitative results on the real-scanned Connect dataset. PointInDI achieves the best scores on both Connect V1 and Connect V2. Finally, we compare model complexity and inference efficiency. Now, I will conclude the presentation. In conclusion, we propose PointInDI, a deterministic iterative framework for high-fidelity point cloud denoising. The framework progressively restores lost point clouds along a continuous degradation path. This design helps mitigate regression to the mean artifacts that commonly appear in single-step regression methods. requirements so that PointInDI can recover cleaner surface, resolve sharp and fine geometric details, and achieve strong performance on both synthetic and real-world datasets. Thank you very much for your attention. I would be happy to answer any questions. Mm. Our network is shown in the not narrow percentage. Point is one. Our network is shown in the percentage one loss and two percentage uh three loss. In the high level loss, our network should be retraining because the loss level is important for network. We show the 10K points and 50K points is to parallel the other baselines. In the 100K points, our methods can our methods have also have a good performance. Uh, According to our fraud interpolation formulas, clean point clouds are not required done in testing. Only the agreed the, only the agreed north point clouds are needed. This is because the network has already learned the degradation path from clean to north point clouds during training, and our network does not need to be retrained when faced with unsigned models. Mm, that's a good question, but I am sorry I can't give you a perfect answer. Uh, Perfect answer right now. But we can have a more in-depth discussion later our lunch. Okay. Uh, I I can understand some features. Uh, our network gives the model uh, a division a, gi- a division path. Its division path can can exactly guarantee the model to perceive the sharper features because the sharp features uh, can be perceived by this formulation.
Hello, everyone. My name is Guanli, and today I will present PoseFusion, a method for multi-view reconstruction from multi-pose captures. The problem we focus on is simple but important. In many captures, the camera can move around the object, but the object itself stays in one pose. In that case, the front and the side regions may be reconstructed well, while the bottom and the contact regions and self-occluded parts are still missing. PoseFusion addresses this by using several object poses. We first reconstruct one neural implicit surface for each pose, as shown in the figure left, the three poses of this Lego trunk. Then align this pose-wise surface and finally fuse them into one more complete surface. Before introducing my method, I first placed this work in the history of multi-view synthesis, in short MVS. Classical MVS methods, such as CoMap, mainly rely on explicit geometry. They estimate camera poses and then use multi-view consistency to recover point clouds or meshes. More recent methods, such as NERF and NEWS, use neural scenes representations. They optimize the continuous field through image rendering losses and other losses, which makes the reconstruction process differentiable. Later methods further improve the training speed, rendering speed, or surface color quality. Here, we can see the rules of multi-view capture and neural rendering. Multi-view capture provides geometry constraints. When the same surface is seen from different cameras, parallax and view consistency help us estimate its 3D position. Neural rendering provides the representation and optimization process. We render images from 3D field and back compare them with the input images and update the field use image loss.
The combination of this is powerful, but it still have a clear limitation. The supervision comes from visible surface is only. If a region is hidden in all input views, the rendering loss cannot reliably recover it. This is a limitation of single-pose multi-view reconstruction. If we take many images from different camera views, the object remains in the same physical pose. For regions such as the bottom, contact areas, or self-occluded parts, more camera views may still not reveal the missing surface. As we can show in the left three pictures as example, the back of this figure, the front of this figure, and the bottom of this figure are reconstructed badly because these are contact regions of the ground. This issue is not only the capability of neural network. The more fundamental issue is that the data does not provide supervision from these regions. A natural solution is to change the object pose so that previously hidden surface can become visible. So we can see why multiple poses are useful. With one object pose, the reconstruction is accurate mainly in the observed regions, as shown in the puppy in pose 1. When the object is rotated or flipped into another pose, different parts of the surface become visible. For example, the bottom of this puppy in pose 1 here and the contact region here in red is invisible, or so it can reconstruct bad. And when we flip this puppy into another pose, we can capture the missing part. This gives us the information needed to reconstruct a complete object. So the main challenge is then no longer only reconstruction itself. Now, it is how to automatically align the neural surfaces reconstructed from different poses and fuse them into one coherent model. So here comes our method, PoseFusion. It has three main contributions. First, it formulates the problem of reconstructing one complete neural implicit surface from multi-pose, multi-view captures. Second, it proposes a coarse-to-fine registration pipeline. We use oriented bounding box, OBB in short, SDF values, and image features to register separate neural implicit surfaces. Third, the paper provides experiments on both synthetic and real captures. The results show that the proposed registration is robust and the final fusions improve the quality and completeness of the reconstructed geometry. And here is our pipeline. Our full pipeline has 4 stages. First stage, for each object pose, we train a separate neural implicit surface. Second, we perform coarse alignment. The stage gives an initial rigid transformation between different poses. Third, we perform fine alignment. Here, image matches are lifted to 3D space and the alignment is further optimized. And here are the results of the coarse alignment and fine alignment. Finally, all poses are transformed into a common coordinate system, and the final fused surface is reconstructed from combined observations. And here are the fusion results of the whole object. Okay, let's move to the coarse alignment. The goal of coarse alignment is to provide a good initialization for large pose changes. The method first extracts a surface from each SDF and computes its OBBs. An OBB has 8 vertices with 3 possible axis correspondence, so we can emulate 24 candidate rigid transformations. The key point is that the method does not just choose a candidate using only SDF samples. It also evaluates the image feature similarity. A good candidate should map one surface close to the zero level set of the SDF after applying this transformation, and its corresponding views should be similar, have similar image features. Notice that we do not refine L course, but search for the minimum L course from 24 candidates. This makes the course alignment more reliable. After coarse alignment, fine alignment reduces the remaining local error. The method first selects the image pairs that are likely to have overlapping visible regions, like this. It then uses ELOFT to extract 2D correspondences between image pairs. After that, we lift them into zero-level set of SDF using ray tracing to 3D space. The final optimization uses SDF consistency, that's SDF loss, and the formulation of the transformation, L rotation. In this way, the two pose-wise surfaces are aligned better than the coarse stage. This slide shows the effect of the fine alignment. On the left, different pose-wise surfaces still have visible misalignment after the coarse registration. After the fine alignment, After the fine alignment, the local structures match much better. The curve at the bottom shows the SDF loss decrease during the optimization. The main message is that fine alignment is not just a small post-processing step. It is important for removing residual errors. Without it, the final fusion may contain ghosting, duplicate cases, or local offsets. Okay, after introducing our method, here comes the experiment part. Before showing the experiment result, let me introduce the dataset for evaluation. It included 11 synthetic models and 7 real-world captures. The synthetic data provide ground truth, so it can be used for quantitative evaluation of rotation error, translation error, and final geometry quality. The real captures are used to test whether the method works well under practical scanning conditions. The average registration time is 4 minutes and 30 seconds. This includes both the coarse and fine stages. For offline reconstruction pipeline, this cost is acceptable. And this slide shows the registration results. The different colors represent the reconstructions from different object poses. The goal is to align them into one common coordinate system. The examples include large pose changes, complex topology, and self-occlusion. PoseFusion still produces consistent alignment in these challenging cases. However, in contrast, several baseline methods such as REGNF, DREGNERF, or Gauss REG are failed to register the certain cases because different reasons. The summary metrics on the right show that the rotation and translation errors remain very low after the registration. And this supports our main design of the choice. Robust coarse initialization and a fine correspondence-based refinement are both needed for the setting. After registration, the final goal is the fusion quality. The left picture compares the input, the ground truth, and the fused geometry and individual pose-wise reconstructions in these colors. As we can see, the fused geometry is the closest to the ground truth mesh, while other single pose reconstruction remains some artifacts. A single pose may reconstruct some visible regions very well, but hidden regions are still incomplete. The fused results use enough observations from multiple poses, so the overall geometry quality is much better. These three metrics on the top also support our conclusion. The fused results have lower transformer distance and higher normal consistency and the F score. The main point is that no single point is always enough. Fusion uses evidence from all poses to obtain a more stable surface. We can see the comparison on the right side video, which shows all single pose results have somewhere reconstruct badly. The bottom, the back of this single pose, and the front of the pose 3. And here comes our ablation study. This ablation study explains why both registration stages are necessary. If the coarse stage is removed, the optimization has no reliable initialization. With large pose differences, it can easily convert to a wrong alignment, so the method fails, as shown in the subfigure B. With large pose, if the core stage is kept but the fine stage is removed, the object is roughly aligned, but local residual errors remain. These errors are still harmful to the final fusion. The full model combines coarse initialization with fine refinement. This is why it produced the most accurate alignment in the example showing subfigure C, D, and E. And E is a close-up view. Our method is robust in many cases, but it still has some limitations. The first limitation is ambiguous OBB orientation. For symmetric objects or nearly symmetric objects, not only in its geometry but also in its color, as we can see in this synthetic and real-world case. The OBB have several plausible directions, as shown in the 3D space example and 2D space example. In such cases, the coarse stage may choose a wrong orientation and the fine stage may not fully correct it. The second limitation is insufficient overlap. Fine alignment depends on the image matching and overlapping visible surfaces. If two poles shares almost no visible region, the matches become unreliable. Therefore, PoseFusion works best when the poses provide complementary coverage while keep some shared visible areas. And we can see in this subfigure, A and B can refine after the course registration, but A and C cannot because this shown in D and E, this is only front and this is only back view, so they have shared nearly no visible regions. Okay, let's have a quick summarize. PoseFusion addressed the missing geometry problem in single pose multi-view reconstruction. Multiple poses reveal complementary hidden surface, and the key is to align and fuse pose-wise neural fields reliably. The method uses OBB, SDF, and image features for coarse registration and fine refinement. It then uses 2D images matches leave to 3D for the fine alignment. And finally, the aligned observations are fused to produce a more complete geometry. The QR code on the bottom links to our project page, where more results and visualizations are available. Thank you for your listening, and I'm happy to answer any questions. I have a question. So, for foods, as you have fields. Uh-huh. So, yeah. It's kind of different. For the mesh itself, it's likely equal, and we have tested whether fuse all the visible regions and the SDF of different poses use the registration results, or fuse the original data set and retrain the fusion neural implicit surface. We further imply the second step because after the further training, we can render the unvisible regions. If just fuse the SDF fields, we cannot, for example, the pose one, we want to render that, we cannot do it. So if you want just a complete mesh, fusing the SDF is enough. But if you want to see the all kinds of view of the object, you need to fuse the original data set and retrain. Yeah. Oh yes. In this, it can be split in two cases. The first case is OVB is ambiguous in, for example, this cubic. This cubic, of course, have multiple plausible OVB as also shown in this failure case, but we can render it successful because it have different face colors. So the image feature can solve that. However, for these failure cases, for example, this toy and this synthetic model, the image feature is also similar when you viewing it in the same direction. So we cannot solve this problem in that case. So that mainly depends on whether the SDF SDF or determines OBB or the image feature. One of them is different PoseFusion can register them successfully. If both of them is unavailable, have plausible settings, our method may fail.
All right. Good morning. Thanks, Congyi, for the introduction. So in this talk, I will present GSurf, which is a hybrid differentiable render method for multi-view reconstruction. And this is a joint work with my PhD students, Baixin, Jiang, as well as my former postdoc research fellow, Jiangbei. So in fact, this work is complementary to the previous talk, PoseFusion. So in PoseFusion, it goes is to reconstruct high-quality surfaces from multi-view and multi-pose captures. Okay, the registration step itself is efficient, but the reconstruction step is quite time consuming because it relies on volume rendering. So in fact, this work is complementary because it has two purposes. Firstly, we want to maintain the high quality of the reconstructed geometry of the surfaces. And secondly, we want to reduce the training time. Okay. So let me begin with the problem statement. So here are given several RGB images of an object or a scene as input, then together with known camera poses. Our goal is to reconstruct a clean 3D surface. The multiple reconstruction is a classic research problem in 3D vision. It has been studied extensively for a few decades. And traditional reconstruction pipelines, which typically are based on computer vision techniques, mainly use instruction from motion and multi-view stereo. So the basic idea for these classical approaches is to match pixels across different views, then estimate depths, then finally fuse the geometry. And these methods can typically generate very dense point clouds, then from which we can apply surface reconstruction tools like Poisson surface reconstruction to obtain polygon meshes. So, however, these methods also have limited capability in terms of appearance modeling. And the reconstruction quality may be low because we can see artifacts such as holes, noise, or inconsistent geometry. So this actually motivates learning-based approaches for multiple reconstruction. Neural radiance fields, or NERF, developed by Maodong et al. In ECCV 2020, was a major breakthrough for novel view synthesis. So here, giving a sparse set of images and known camera poses as input, a NERF learns a continuous volumetric representation of the entire scene. Then by volume rendering along camera rays, NERF can synthesize very high quality novel views from arbitrary viewpoints. So basically, NERF is very strong for rendering, but the important question is, does this also give us accurate surface geometry? And the answer is not directly. So NERFs actually can learn radiance and density fields, and these two are very good for rendering purposes. However, they do not explicitly represent a surface. So usually, if we want a mesh from NERF, we need to threshold the density field. But this threshold typically is very hard to choose. So here, if you see this Zhao model from the famous DTU benchmark, you see that if we set the S value of the density field, sigma equals 1, 50, and 500. So none of the extracted SO surfaces represent a clean, high-quality geometry. And also, the density fields is often very noisy. So volume rendering basically can tolerate this noise because volume rendering is based on integration. This integration nature allows volume rendering to integrate along rays and can hide some of this noise in the final render images. But if our goal is to reconstruct a surface from the density field, then this noise becomes visible. So they cause artifacts and inaccurate geometry. So NERF is excellent for view synthesis, but it is not ideal for if our final target is clean, high quality surface from the multi-view images. So to address this problem, neural implicit surface methods such as NUS and volume SDF introduce an explicit surface representation into the neural rendering pipelines. And they replace the density field with implicit functions, usually a scientific field or SDF. So an SDF is useful because the zero level set directly defines the target surface. It also allows us to define regularization. Such as use the Econo Econo constraints, which is the first order constraints, or even using the singular Hessian constraints, the second order constraints. So this regularization allows us to obtain smooth, high quality geometry. And these methods jointly optimize appearance and geometry, so they can produce much cleaner surfaces than basic NERF. But these methods rely on volume rendering. So this means that they still need many resamples and many MRI queries in order to produce a single image. So this can be very time consuming. So neural implicit surfaces give us high quality geometry, but they're slow. For a typical scene in the DTO benchmark, training may take more than 10 hours. And to be honest, this is very slow. This is very slow. So this creates a trade-off. We can get very high quality, strong geometry quality, but the efficiency is limited. So this motivates our work. Can we keep the geometry quality, but greatly reduce the runtime? So this is where Gaussian splatting becomes attractive. And 3D Gaussian splatting represents a scene using many local Gaussian primitives. So instead of sampling densely along camera rays like in volume rendering, so 3D Gaussian splatting projects these primitives to the screen space and then use alpha blending to compute the pixel colors. So this can be implemented very efficiently with CUDA rasterization. So training is much faster comparing to volume rendering based approaches, and rendering can also be done in real time. But there's one key limitation. So these Gaussian splats do not inherently form a continuous surface. They're discrete. So 3D Gaussian splatting is very efficient, but the geometry is not as clean or explicit as an SDF. Now we have two useful ideas. Okay, so on one side, neural-interface surfaces give us a continuous SDF geometry. Okay, but they're slow because they rely on dense volume rendering. On the other side, okay, Gaussian splatting is very fast, okay, but the Gaussian primitives alone do not define a continuous surface. Okay, so the key question is, okay, can we get continuous SDF geometry without reintroducing volume rendering? Okay, so this is the key question. And GSurf actually answers this question by moving SDF supervision directly into the splatting branch. So this slide gives the high-level idea of GSurf. So we introduce SDF inside the 3D Gaussian splatting rendering pipeline, but instead of adding an extra volume rendering branch, we supervise the SDF directly using Gaussian primitives. Okay. The main challenge is that Gaussian centroids must be reliable. Okay, imagine if the Gaussians are not very high qualities, they're noisy, they are semi-transparent, or they're just float away from the surface. Then these Gaussians actually provide very bad supervision, which can mislead SDF learning. Okay, so GSurf, the main goal for GSurf is to make these Gaussians reliable enough so that they can act as surface anchors. And this slide shows the four key components of GSurf. And firstly, we treat Gaussian centroids as candidate surface anchors. And secondly, we use opacity entropy regularization and to push the opacity towards two ends. Okay, either 0 or 1. Okay, 0 means these Gaussians are completely transparent, so they can be ignored. And 1 means that they're opaque. Okay, then we'll apply a threshold to filter out all low opacity Gaussians. And thirdly, we supervise the SDF so that the reliable Gaussian centroids lie exactly on the zero level set. Last but not the least, we use SDF normals and the geometric features to help with color prediction. Okay, so the key design choice is SDF learns from reliable 3D anchors, not from the actual remarching based volume rendering branch. Okay, so this is the main reason that GSurf is able to keep the efficiency of 3D Gaussian splatting. And this is the whole training pipeline. Okay, so the image reconstruction loss optimizes the Gaussians from the multi-view images with the RGB color as supervision. Then at the same time, we have the entropy loss. Okay, so this loss pushes opacity towards two ends, either 0 or 1. And this loss helps remove weak transparent primitives. Okay, then in the remaining Gaussian centroids are used for supervising the SDF zero level set directly. Okay, and the SDF also provides useful information like normals and geometric features. So we use these features, we feed these features into the appearance module to predict better view-dependent colors. So everything is optimized within a single splatting branch. Okay, we do not use a separate volume rendering branch. Okay, this is actually the key difference between our method, which is actually a hybrid method between Gaussian and volume rendering. Okay, there are other existing approaches which uses SDF and Gaussian together, but they have two branches. Our method only relies on one branch. And we have one practical issue to consider in our experimental results and implementation. Okay, so we call this a cold start problem. So at the very beginning of the training, we observed that the initial Gaussians, which are typically from structure for motion or even from random initialization. So these primitives typically are very noisy. Okay, if we use them directly to supervise the sun density field immediately, then the SDF may learn a wrong surface. Okay, so in our implementation, we consider this so-called a cold start strategy. Okay, so we delay SDF activation. And in the warm-up stage, the image loss and opacity regularization first clean up all Gaussian primitives. All the local opacity primitives are removed. Okay. Then after that, the SDF sees more reliable anchors and training becomes much more stable. So in our implementation, this delayed activation starts SDF learning after the first 500 iterations. Okay, so we use these hyperparameters for all the experimental results in our paper for the DTU dataset and MIP NERV 360 dataset. And this strategy helps avoid early optimization clash. And this is actually one of the core ideas in GSurf. Okay, so low opacity Gaussians, they may not affect rendering very much, okay, because rendering is actually based on alpha blending. If a Gaussian has low opacity, so it does contribute little to the final pixel color. However, these Gaussians may affect SDF learning significantly. Okay, this is because as SDF treats these Gaussian centroids as surface samples, if many centroids are just floating in the space, they're not on the surface, then SDF may learn around surface. Okay. So GSurf uses entropy opacity regularization to push Gaussians towards being either opaque or transparent. Okay, so the density is at just zero, opacity just 0 or 1. Okay, and then low opacity Gaussians are filled out. Okay, then after this, the remaining centroids become much more reliable because they can serve as surface anchors. In our experiments, we observed that, okay, so this strategy is highly effective in terms of reducing transparent Gaussian significantly. Okay, so here, if you, anyway, so if you check, where's the pointer? Okay, if you see the bar chart, okay, the bottom one is our full model. Okay, so the number of transparent Gaussians with threshold below 0.5 is only 1,000. Okay, the overall number of Gaussians is more than 43,000. Okay, so this ratio is extremely small. If you check the baselines, for example, the 2D Gaussian splatting, okay, so the number of transparent Gaussians is significant, okay, 24,000 comparing to the remaining one, which is 36,000. Okay, and also our ablation study justify the effectiveness of this regularization. And this conversion table is very dense, so I would not read every entry. And here, the main thing is just the final row, okay? So compared with other GS plus SDF methods, to be honest, there are many other methods which consider using both Gaussian splatting and Sun-Dinson fields together. Okay, so comparing with these approaches, so GSurf keeps a single splatting branch. Okay, all the other methods, they adopt 2 branches. They use Gaussian splatting as well as volume render together. Okay, and GSurf has only 1 branch, which is based on Gaussian splatting. Okay, so it supervises the SDF at Gaussian centroids, then also use geometric regularization, okay, such as Akano and normal regularization. And the time complexity, okay, is proportional to the number of Gaussians, okay, instead of the number of rays multiplied by the number of samples. So that is the complexity for volume rendering-based approaches, because we avoid volume rendering at all. So our time complexity is proportional to the number of Gaussians. And from the results, we observe that the number of Gaussians is a few. Okay. So here, the message is GSurf is able to keep the efficiency of splatting while still learning continuous SDF geometry effectively. Okay, so let me show some real results. And this slide shows 3 representative models from the DTU benchmark. And in many baseline methods, we can see artifacts like holes, noise, or fragmented surfaces. And GSurf gives smoother and more complete surfaces comparing to the baselines. And also GSurf can preserve important geometric details thanks to the use of Sun-Dinson fields. So the main takeaway is that GSurf achieves a better balance between geometry quality and efficiency than the baseline methods. And GSurf is not limited to object level reconstruction. So here we also show indoor and outdoor scene level results. So compared to with GSpool, which is a method published in NeurIPS 2024. Okay, so GSurf actually produces surfaces that are less fragmented and preserve finer structures. So this actually demonstrates that GSurf can scale beyond isolated objects to more complex scenes. And this ablation slide shows why opacity regularization is critical. Okay, if we remove geometry-guided appearance, okay, so this actually only causes a modest quality drop. Okay, but if we remove opacity regularization, so we see a significant quality degradation. Okay, the chamfer distance actually increases from 8.97. Okay, this is for the full GSurf model to 21.83. Okay, so if we do not use opacity regularization at all. Okay, so this means that the anchor assumption breaks down when opacity is not controlled. So the entropy and the pruning design is not just a small detail. Okay, in fact, they are the key mechanism that can make the direct SDF supervision from Gaussian this process very stable. All right, so in conclusion, GSurf actually connects continuous SDF learning with discrete Gaussian splatting. And the main idea is to turn Gaussians into reliable surface anchors using entropy, opacity, regularization, and pruning. Then we can supervise the SDF directly from Gaussian centroids without adding extra expensive volume rendering branch. And finally, SDF normals and geometric features also help improve appearance modeling and geometric details. Our code is already online, so you can scan the QR code to access the GitHub page. Okay, and thank you for your attention. Actually, 500 is the experimental a heuristic number. So my student just simply try this. Yeah, actually, I didn't know whether if you change this 500 to 200 or 1000, so how come the result would be? I don't know. Yeah, so this is a purely experimental result, and this is heuristic. Yeah. So for all the detailed benchmark, and we try this 500, it seems it works pretty well. Yeah, but for other data set, some other numbers may work. Yeah, we don't know actually. Yeah. Yeah. This is standard one. Yeah. Actually, because here, good point. So for SDF is a key component in the whole optimization pipeline, and we supervise SDF by using Gaussian centroids. But we do not use all the Gaussians because some Gaussians may not be the ideal ones, so they may float in the whole space. They have very low opacities. So after removing all these Gaussians, then the remaining ones, we consider these are reliable geometry priors. So we train the SDF so that these Gaussians, okay, lie exactly on the zero level set of the SDF. Then, of course, to learn SDF effectively, we can apply regularization like Akeno or some other regularization. Yeah. Next, please. Uh, I should ask my student. I don't know. Yeah. This is the implementation details. Yeah. I believe that it's just a single neural network for one escape. It's not hierarchical. Yeah. Mhm. Yes. Yeah. Mhm. We have the CD. Let me see if these numbers are the chamfer distance. These numbers are actually the number of Gaussians. Actually, in the paper, we have the quantitative metric. We have both chamfer distance and the normal consistency. Yeah, because these models are from the Omni 3D dataset, so we have ground truth geometry. Yeah. Okay. So besides the visual checking, so the quantitative metric also reveal the high quality of our approach. Yeah. Oh yeah, shock features. Yeah, yeah. Uh, uh, yeah, this is a good point. Yeah, actually, next week, in SIGGRAPH 2026, we'll actually present a paper. That paper is called ShockNet. Okay, so ShockNet is a variant of the conventional multi-layer perceptron. So in ShockNet, we're able to represent exact perfect shock features within neural network. But this one, okay, this is just based on conventional MLP, so we do not preserve shock features. Yeah, so it looks sharp, but conceptually it's still smooth. Yeah, good point. Yeah, yeah, of course. Okay. Yeah, thank you.